Welcome back, folks. We're going to talk about our next value and variable, and that value is voltage. If we're going to move charge around, then it's going to take energy to move that charge. Certainly, if we're going to do work and convey information, we don't get those things for free. We got to expend some energy, and the form of energy we're going to use to move charge in an electric circuit is voltage. Okay, so from your prereq courses, you may recall that voltage is a form of potential energy. Okay, so I'm hoping this is bringing back some of those wonderful memories from physics for you of potential energy. Okay, and we have to think about how we quantify potential energy from those physics courses and maybe relate it to what we're doing when we're analyzing circuits. Okay, so if we're going to find the potential energy of an object, and it's got to be a simple object because I need to be able to draw it, so we're going to go with an orange ball like that, and one of the things we want to measure about this ball is its height above the ground. Okay, and I did this just for you. I'm excited about it. I figured out how to make little grass on the ground. Look at that. That's the ground. Okay. Happy little grass. So I'm in a basement by myself, okay? That's making my day. Give it to me, please. All right, so what we're interested in is the height above the ground. Okay, we're going to call that h. Okay, lowercase h for height. The ball itself might have some mass, and then depending on what planet you're on, there's going to be some gravitational constant. So we would talk about that potential energy as capital E equals mgh. Okay, and voltage is not horribly different from this. We have to measure the distance from the object to some reference point. And the reference point here is going to be our ground. Okay, so let's scroll down here and make up another problem. Let's take two balls. Okay, oop, made that a little bigger. I'll try to make the next one to match. So one's red, one's blue, and we're going to hold them at roughly the same height here. Okay, and we'll get the grass again. That's what I'm talking about with production value right there. It's good stuff. Okay, and if they're at the same height, okay, if the two balls are at the same height, then they have the same potential energy, right? The same height. They have the same potential energy. Sneak an eye in there. Potential energy. Or so we would think. Okay, so they have the same potential energy. Right up until the point where, I don't have brown, we'll go with orange. Somebody comes over and places a table. And this is going to be my table, okay? No making fun of it. Look at that. It's a table. It's like a picnic table. You're out in the grass. It's nice. It's summer outside right now. Oh, you can't see out that window. So let's make sure we're all on the same page that that's a table. Okay. So now which one has more potential energy? Okay, they're at the same. They're level with each other. Okay, they're level with each other, but the blue ball has more distance to drop. So we have to consider how far that one's going to drop, and how far that one's going to drop. And in this case, the blue object has more potential energy, and it all comes down to what we're using as a reference. Okay, what do we call 0? How far is it going to fall? There's some similar concepts between the mechanical side of life and the electrical side of life, and they're all brought together by physics. But it matters where you're, what point in your system you're using as a reference. So we got to measure this potential energy across some distance. Okay, and we're going to have the same kind of thing pop up when we're talking about voltage. We can't just talk about the voltage in a circuit at a single point, which we're going to call a node. We have to say, what's the voltage at this point with reference to something else? So we measure the potential energy, okay, in the case of circuits, we're going to say it's a voltage, but it is a potential energy as well, is measured across some distance, or it's 2 points in a system. Okay, and this is important. Measured across some distance. Okay, but I really want you to think of it or between 2 points in a system. Okay, so for our simple example here, the first point might be where we're dropping the ball from, and the second point might be where it's going to stop. Okay, and this one's going to stop at a different point, so it's going to have less potential energy. In a circuit, I said we can't just measure the voltage at an individual node. We have to know that we're measuring the difference between energies at 2 different nodes, and I'll formally define a node in some future videos shortly here. But this idea of a reference matters. Okay, and in an electrical system, we're going to call it ground. Where did we get that name? Well, we don't have grass growing in a circuit, but it's the same idea that it's 0. Okay, now MEs might call it a datum line. EEs are going to call it a ground. It's really 0 potential energy. Okay, in a schematic, there's more than one type of ground. For circuit analysis, for the most part, and certainly for this class, we almost don't care. We're just saying that's the node that we're calling the reference for every other value in the circuit. But as you look at schematics, you might see different symbols used as ground, and you may have faculty members in different classes that use the different symbols. They all have meanings, and I just want to make sure you're comfortable with all of them. Okay, so the first one I'm going to talk about is drawn like this, and we've got 3 lines. So it's a line, and we've got a vertical line and 3 horizontal lines, and this is called an earth ground. Okay, and the purest meaning of earth ground is that the ground below us ends up being a node in your circuit somehow, usually through your electrical system in your house or your office or wherever you're plugging things in. But really, you take a big metal rod, you pound it into the ground, and you hook a wire up to it, and then you connect it to your circuit somehow. That's the purest meaning of an earth ground. It does get used in a lot of various ways. I always found it funny when I was working in aerospace and I would look at a schematic and it would have an earth ground on it. Now, how does this thing have an earth ground on it? It's flying in the air. Like, there's no way that it's pounded in, a rod pounded into the ground. We're just not going to connect that to a helicopter or an airplane. I've also seen or heard that it shows up on schematics on various types of boats. Same kind of problem. It's a boat. It's floating in the ocean. It's not connected physically to the ground. So the earth ground by standard, so if you go look up the IEEE standard for schematics, the earth ground is allowed to be used as a general ground, the biggest hunk of metal that you can find. So it might be the chassis of the helicopter or the chassis of the boat that you're using as a ground. So I think it's kind of funny that it's called earth ground, but then it's not used purely in that way. So you're going to run into that one. The one that I like to use, because I think it has the least meaning attached to it, and if all we're doing is circuit analysis, This is the one that I prefer, and this one is called the signal ground. Okay, and it's just a vertical line with a little triangle on it. So you'll see my schematics look like that more often than not. And all it means is that node is 0. Okay, and that's it. And that's what I like about it. It doesn't have any other implication for it. So the other common type of one that you're going to see is a chassis ground, and that ground looks like this. Okay, these come off at a slight angle, and that's called the chassis ground. Okay, and the chassis ground is exactly what it sounds like. It's the chassis of the device you're using. So if we're looking at the power supply like we did in the last video, then it's going to be the chassis of that electronic device. And there's reason to do that. You might want to ground to the chassis to provide shielding. It can prevent shock if it's done correctly. So there's reasons to connect to the chassis ground. And if I were doing that for those reasons on my schematic, I would want to indicate it as a chassis ground. Okay, so there's different kinds of grounds. Now, circuit analysis, because that's the class you're in right now. All of these indicate the 0 volt potential energy point in the circuit. Okay, and that's all we're going to use them for. And because of that, most of the time when I draw my circuits, I choose to draw the signal ground. Okay, kind of right there. Oop, I'm off my camera. Right there on the bottom. Okay, so that's ground. Think of it as your datum line if you're doing a dynamics problem. Okay, so just like with our current supply, if we want to draw a schematic that has a device that does these things, then we have to have some schematic symbols. Okay, we want to abstract our circuit, and we need a device that creates voltage. So this one gets 3. Who's excited about that? Okay, 2 of them are independent. So let me draw those over here. Independent. Okay, voltage supplies or voltage sources. Okay, what's nice about this, the first one's nice and easy. If you were paying attention in the current supply video, it's also a circle. So that circle tells me that it's independent. And that kind of lines up nicely. And we have our lines that we can connect to different parts of the circuit. And on the inside, we're going to have plus and minus. So that if you see a plus and a minus, you know that it's a voltage source. Okay, if I see a circle, I know it's independent. If I see the plus or the minus on the inside, I know it's a voltage source. Okay, this node has more potential energy than this node down here. All right, and it's going to be a constant. So we can give it a part designation Vs, and it has a constant voltage. Let's say 12 volts. That's a common voltage that you're going to run into in a lot of circuits. Your car is going to run on 12 volts. If you have a boat, then you make more money than me. But you have a boat. Good for you. It might run on 12 volts as well. Okay. Now, this is a little bit general, doesn't imply anything other than it's a constant voltage source. The other independent voltage source that you may run into, and we treat it as an independent voltage source, is a battery. And that gets its own schematic symbol. It has one long bar and it has one short bar, and it looks like this. Okay, you may get a little plus up there to indicate that the long bar is the positive side. It's the one with more energy. But this, again, we treat as an independent source, and that could be a 12-volt battery. All right, that symbol these two symbols get used interchangeably in a lot of cases. I'm going to use them both. I'll use them both in the same problems. You need to get used to seeing both and understanding how to analyze circuits with both symbols. So I'm going to mix it up so that you get used to figuring out what's going on with that. You may see a battery drawn with multiple cells. You might see it drawn like that. Okay, that would also be a battery. That's a multi-cell battery. Again, the long bar is the positive side, and the negative bar, or the short bar, is the negative side. Those are all the, maybe not all the independent sources. Whoops. But certainly the common ones. Drop my pen, sorry. And the dependent current sources, or voltage sources, well, there's only one. Okay, so once again, all the independent ones, I can walk over to the bench supply. It's the same one that we looked at in the current video. And we can hook that up. Okay, and I'll hook up the red post to the positive side of the schematic symbol and the black post to the negative side of the schematic symbol. It's a physical thing. I can put it in your hands and you can touch it. Same kind of comments about the dependent voltage source. We use it to model amplifiers. Amplifiers, transistors, which can be used for amplifiers, control systems, you might run into them there. Okay, all the same comments. This one's dependent. We know that because it's a triangle, and it's a voltage because I'm looking at the plus and the minus inside that, not a triangle, it's a diamond. I'm looking at the plus and minus inside that diamond. Okay, now it's still a voltage source, and it could be labeled as 4Vx, which I believe was the same as before. So this one's going to put out a voltage dependent on a voltage. Okay. Now you may also see it labeled, so it could be labeled for Ix. We could have a current controlling this voltage. Okay. But when we analyze the circuit, we've got to look at the symbols inside and we say this is a voltage. It puts out a voltage. It may be dependent on a current, but this is a voltage supply. And we're going to treat it as such. So always look at the symbols inside the shape to tell you what kind of source it is. All right. Some other types of voltage sources you may run into. We really do this in order to clean up schematics, because too many wires can actually make things look cluttered, and they're called label voltages. Okay, they're pretty common, so I think they're worth noting. And you're just going to see them drawn as a bubble with a little stem on it connected to the rest of the circuit. So if I have a plus 5 volt source, it might be a bubble with that little stem. I could have a bubble with a 12 volt source. You may see them drawn upside down, pretty common for negative voltages. Okay, oops. So if I have negative 12 volts like that, you may see it drawn upside down like that. These are the same voltage sources, but a lot of times it gets glossed over, and because it gets glossed over, I want to mention it now so that you know what you're looking at. So I'm going to draw the simplest schematic I can because we're not too far into class yet. But if I have a labeled voltage like that, and I connect it to a resistor, which we'll talk about in a little bit, and then I ground the other side, okay, and I say this is 5 volts, and it doesn't really matter what the resistor is for this example. I want you to know that you can take that labeled voltage, and as far as circuit analysis is concerned, you can replace it. Okay, so I can say I can take that resistor and the ground and the voltage source up here. Now that voltage source it's just labeled 5 volts. That's 5 volts in reference to ground. Okay, and that's why the ground is so important, because it's 5 volts above the ground. And you can connect a voltage supply. Ooh, I drew a battery that time. That's just what came out of my soul when I decided to draw a voltage supply. So I can say, hey, there's a 5 volt battery there. Okay, and these are equivalent circuits. Okay, this 5 volts is in reference to ground, so it's 5 volts above ground. Okay, so these labeled supplies you're going to see a lot when you deal with amplifier circuits and things like that. But when we deal with circuit analysis, I want you to know, if you're confused by it, draw the supply in. Okay, connect one side to the node that has the labeled voltage supply and connect the other side to ground, and then do your circuit analysis. So we may see voltage supplies labeled this way in circuits. Okay, so we have electrons flowing in one direction, holes flowing in the other direction. We're pushing them with voltage, but we have to push it through something. Okay, and we're going to push it through all sorts of materials, but we need to talk about the properties of those materials as we try to make this charge flow in a way that's useful to us in circuits. Okay, so we're going to answer some questions in web work about this stuff, and then we'll move on to the next video, and we'll talk about the first property that we're interested in as we make charge flow through things. Okay, so stay tuned and good luck. I lied. I forgot something. I'm back. I think I got everything lined up. It's a day later. Can you tell by I'm wearing a different undershirt? We're moving. We need the definition of voltage. I think I've said it, but I think we need the actual formula, and we need to summarize things a little bit too. Voltage is going to be the quantity of energy it takes to move some quantity of charge. So we get the charge derivative of the work done necessarily to move that quantity of charge. So we need that. We need that when we talk about power, and I totally forgot it until I went to record the video on power. So there's that. The other thing that I want to make sure I'm doing so that I'm consistent is when we talk about voltage, we don't forget about poor Alessandro Volta, and the unit, of course, is the volt. Okay, and the variable we're going to use, if you haven't figured it out, is capital V or lowercase v, and I put a tail on my lowercase v so that you know it's lowercase. Okay, so I wanted to clean that up for a little bit for you. I mean it this time when I say stay tuned and good luck.